Pick me back up for the remainder of the afternoon. I recommend it. And we'll go and have the actual results of the competition in a little bit. But before we do, I want to get you guys takeaways. What kinds of things stuck out to you as you were working through the kind of simulated data science exercise? What was, again, we're trying to get a big picture overview of what we're going to be doing in detail for the rest of class. But as you were working through it, what jumped out at you guys?
There's a lot of information taken at once.
Okay. So lots of information. Yeah, so in what way was it a lot? Like what was kind of overwhelming about it?
Well, I think you had come in part of the way through, and our group was just trying to understand what was going on from like a standpoint of like what are we doing to the data and the different. There's a logistic regression and the other two different kinds of trees, and we were just trying to understand what those did and how they worked.
Yeah. In classes and models, that was, and again, if you didn't understand what any of the models were doing, I think probably you guys have logistic regression down now. But if you didn't understand what any of them were doing, it's okay. We're going to cover in detail what all was going on as far as the models were. But there were a bunch of different classes and models. I could have added more. So just be grateful for that.
I'm sure.
Okay, so different classes and models. What else jumped out at you guys? Weston?
Sure. I think that we talked about this one, but just the fact that certain models would drive towards fitting the training data, whereas the other ones would actually fit the test data, and you'd get radically different answers.
Okay, so let's talk a little bit about this idea of training versus testing data. What did you generally see happening? You said you were going to talk about some models kind of driving more towards the training data versus the testing data. Expand on that idea.
So at least an example from the code itself was let's see, it's the last model type. It was the XGBs. That one always fit the training to a T, but at the expense of fitting a broader set of data.
Okay, so it did really well in the training. What does this mean?
Overfitting?
Overfitting. What is overfitting?
You're trying to account for too many data points as opposed to trying to create a generic curve. Right?
So can you put that in different words and say it again?
Where I think of overfitting is like if you have 5 data points, you don't want to create a quintic function.
Quintic function's a big word.
Extra fit function.
Okay, so we've got these data points here. There's 5.
Yeah.
So what would be an example of why don't you come down, Ryan, and draw an example of an overfit function?
Okay.
I primarily have you guys come down and draw something so you can see how hard it is to draw on a blackboard, so you don't judge me as much when it comes time for me to draw things. Okay, so why is this overfit? It looks pretty good to me. It does great.
It fits the points more than it fits the actual trend of the data.
Well, what does it mean to have a trend in the data if not to fit the points?
If you had more points, it may look like they're not fitting that model, but.
I see. So the next set of points might look something like this. Maybe I should have used a different color. Okay. So what's the problem with that?
You can't predict well with the curve if the trend isn't well defined.
Okay. Well, so in what way is the trend not well? Well, let's be more precise in trend.
You want to accept more data. So I think what we talked about before was if your model fits the data you provide it, when you take new data in, it's not going to predict. It doesn't predict for the new data that comes in, even though it should.
Okay, so in some sense, we don't really care about how well it does on past data because past data is in the past. What we really care about is what it's going to do in future data. So right now, this model here is doing really good on these white points, right? But so we got new data, and the new data is the orange points. What's the problem with this?
It's a bad predictor.
Okay, it's a bad predictor. What would be a better predictor of the orange points? And I'm going to make whoever is willing to do it come down and draw it. Andrew, come on up. So those don't get anywhere close to the points.
It gets close enough to them. It gets equally close to all the points.
I see. Okay. Well, I mean, you could have drawn something that connected all these dots instead, right?
I could have. I'm not a maniac.
So, I think we probably will all agree that this line right here is a better model, but it's actually worse on the white points. And we could have like connected all the points and drawn something that was super squiggly. Why do we generally consider this a better model?
Occam's razor.
Okay, expand on that.
Simpler is better.
Simpler is better. Okay, this is actually a really important premise in machine learning. Is that in general, unless you have a compelling reason to use a more complicated model, a simpler model is better. You had all these regularization parameters, and these were basically different parameters that would tell the model how much to weight simplicity versus complexity. And you didn't necessarily understand what each of those were doing, but at their core, they were all biasing the model either towards or away from simplicity. So with XGBoost, you found that it did really well in training. So in some sense, it was doing this connect the dots thing. Was anybody able to rein in XGBoost?
What do you mean?
Like, so, you know, the idea is, so I think what Weston was saying is that XGBoost tended to overfit, right? It tended to overfit, and it tended to do well in training, but I'm assuming not super well in the testing. Is that right?
It would be sometimes half of what the random tree would be.
So this was a model that was overfitting. And so you had those parameters to rein it back in, to keep it biased towards simplicity. Was anybody able to hold it back in some sense, to keep it close enough to simplicity to make it work? Why?
Because none of the metrics accurately predict bad bar.
No, I mean, they do. I mean, these will, you guys got models that work. I've already peeked at the score, and I know there's some good scores up there. So you guys got models that work, things that do predict. XGBoost is a model. Presumably you could get it to work. But what was kind of standing in your way?
We didn't know how the parameters that we were inputting were affecting the output.
Okay.
That's good.
So one thing is we didn't really understand the parameters. Anything else? I mean, you can always try things, right?